This video will be talking about how to construct something called an ice table. All right, so we're going to write it in a nice, cool blue color. How about that? Okay, so thing to understand, this is really kind of a way of bookkeeping, keeping things logically ordered so we can make as few mistakes as possible. So the chemical reaction we're going to use is a very important industrial reaction. If it wasn't for this reaction, we wouldn't have enough fertilizer to grow all the food to feed 7 billion people. So really, really super important. And it actually is estimated to use about 10% of the world's energy to produce this, and it's ammonia. Okay, so ammonia is used as a precursor to various fertilizers, including ammonium nitrate. So the stoichiometry is 1, 3, and 2. And so we're going to look at a problem. And let's say, okay, we're going to put start with, okay, so start is initial. All right, and so we're going to write down how much nitrogen and hydrogen and ammonia we have to start with. And so the quantities we're going to use are uh, 0.040 moles of nitrogen, 0.010 moles of hydrogen, and let's say we already have some ammonia there, also 0.10 mole. Okay, that's the number of moles. Now, unfortunately, the equilibrium constants in terms of molarity, we actually need to know what is the volume of this system. And if we say it's 2.0 liters, then the molarity is going to be moles per 2 liters. Okay, and so let's go ahead and write down the molarity here. And we'll actually just go ahead and write it down in the initial line. 0.020 molar, okay? This divided by 2 will be 0.0050 molar. And the last one will also be 0.0050 molar. Now, the important thing to realize is that the initial amount has nothing to do with the stoichiometry. These are just completely random numbers based on some point of time, some mixture we have. Okay, now the next thing that happens, first of all, we probably aren't at equilibrium. It would be extremely unusual occurrence by chance just to happen to be at equilibrium when we just mix a bunch of stuff together. So now the other thing that we have to know is a little bit more information, all right, because we don't know anything about the equilibrium that's going to be established or the equilibrium constant yet. This problem is going to be one where we finally wind up with, at equilibrium, so this is the extra piece of information that gives us the ability. At equilibrium, we'll have 0.020 mole of hydrogen, which means the concentration will be this moles divided by that many liters. And so finally, okay. Now this is like balancing your checkbook, if you do that sort of thing anymore. You have your beginning and you have your ending, and then of course the changes that produce how you get from the initial to the final equilibrium. Okay, so now we know that the hydrogen concentration is going to go up. It's going to increase. And so I'm going to choose the sign of the amount that hydrogen changes. Okay, so this is the initial. This is at the equilibrium or the final state for the system. This is the change. Now the change is the stoichiometry. Okay, so it's very important for you to understand chemical reactions are describing changes only. And so, for example, if you use the analogy of, meat and cheese and bread, the stoichiometry is 2 breads, 1 slice of meat, 1 slice of cheese. And if you have no bread, you're going to make no sandwiches. If you have a lot of bread, well, you'll have some bread left over, all right? And so, but the chemical equation just says, hey, if you're going to make 1 sandwich, you need 2 slices of bread, 1 slice of meat, 1 slice of cheese. And whenever you run out of one of those, that's when you stop making sandwiches. All right, so we know that for hydrogen to change by some amount, nitrogen has to change by 1/3 of the amount, because our recipe for ammonia says you need 3 of these for every 1 of these. So the ratio, so it doesn't matter what the number X is, we'll determine it, but it has to be 3 times larger for hydrogen than it is for nitrogen. And this also has to be 2 times larger than nitrogen, because it's a 2-to-1, but it's important for you to realize it has to have an opposite sign. So if we're making these from these, we're going to increase the amount of this, we're going to decrease the amount of ammonia. Okay, it's a very common sort of error to make. Now the last thing is that we just add these 2 in every column and see what we get. Okay, these 2 add to this expression, but that is a number we already know in pink here. These 2 add to give that expression, but we don't know what this number is, but we will soon. And these 2 add to give a certain number. Again, we don't know the number yet. So this tells us nothing. We know nothing about this. However, this, we know the number, so we can solve for X. Okay, so it's a super easy algebra. Okay, 0.010 equals 0.0050 plus 3X. Okay, so X is going to be 0.00166 forever. And now we know X, we can actually get this number. And so we put this number into here, and it turns out that just by coincidence, it is also 0.00166. And this one is going to be the sum of the 2. All right, so we have every concentration. Okay, so I'm going to circle them. The hydrogen is that concentration. The nitrogen is that concentration. The ammonia is that concentration. Okay, so now from the fact that we knew all the initials and one of the final, that allowed us to determine all the final concentration. Now once we have all the final concentrations, we can calculate the equilibrium constant. That's the reason for this problem. All right, and so writing the equilibrium constant is very easy. It's the products to the stoichiometric powers divided by the reactants to their stoichiometric powers. And we simply substitute the numbers in here. So ammonia is going to be that number. Nitrogen will be this number to the first power, and hydrogen will be that number cubed. And so the equilibrium constant is going to be 130. Okay? Now, so we round it off to two significant figures because that's really all the figures we have of significance in this problem. Okay, so this reaction is, for this particular temperature it was run at, slightly product favored because K is greater than 1. It's not a huge number, but it is product favored. However, you can see that even though we called it product favored, we actually have less product, 0.001 something, than we do of the two reactants, 0.01 and 0.02. And the reason that occurs is because the denominator has a total of something to the first power, something cubed, whereas the numerator only has something squared. So even though the number's smaller, if it's smaller and then gets, you know, something to the first and something cubed, then actually will make the number larger. All right, so that's what you have to be careful with in the language and the understanding of what we mean by product favored. All that means is that we have a K greater than 1. It does not mean that we actually have more product.